Hi, everyone. Today we're going to be talking about the validation set approach. This approach really can be used for any type of algorithm, but we're really going to be focusing on classifiers today. And the motivation behind the validation set approach is that we want to know how well our classifier performs in the real world. And I think this is the important part, right? We want to know how it performs in the real world. In general, when we have an algorithm, we usually estimate it with some data, right? So we start with some data. And maybe your data looks like this, right? We're doing classification. So let's say we're trying to predict some y, which this y really could be anything, right? But in this case, it's a label 1, 0, 1, 1, 0, something like that. Maybe in this case, the 1 implies you should get a loan, or you will pay back that loan, and 0 implies you will not get that loan, or will not pay back that loan. And your goal is to predict this y, and you have some features. So x1, xn, I'm just going to call these my features. And again, these really could be anything. These could be like age, maybe this one could be gender. This could be the amount of money you have in your bank account, things like this. All right, and this is the data that we have. And remember, the setup, the general setup we have is that we know these labels ahead of time, right? So we have a data set where if you give me someone's age, let's say you give me someone's age, the amount of money in their bank account, their gender, I also know, associated with that information, whether or not I should give them loans. I know what's happened in the past. So this is important. We're going to use this in a validation set approach. This is something we know what happens in the past. And this is really nice because you can imagine that this y, these y's, can be used as a scorecard. And I'll show you how we do that in a second. So in a sense, we want to do two things with this data. The first thing we want to do is we want to estimate our classification model. And the second thing we want to do is we want to grade our classification model. In the sense that we want to know how it would perform on data it's never seen before. Okay, and that's what we mean by grading. Okay, so this means we're going to use our data twice, right? And since we're using our data twice, you can imagine that we don't want to grade our classification model on data it's already seen. We want it to be graded on data it has not seen. So to do this, we're going to do something that I think is quite simple, and you've probably done this already yourself, is I'm going to take this data set. Oops. So I'm going to take this data set, right? Boom, boom, boom. And then I'm going to divide it in half. That's what this red line is. I'm dividing the data set in half. Right, and this data set, so just so we remember, there's a y here, x1, our features. Right, I'm going to divide this in half, and then I'm going to color this first part blue. Kind of try to shade that in there, and I'm going to color this bottom part green. Let's do orange, so it's a different color. This bottom part orange. Okay, so what am I going to do with this now that I've divided it in half? Well, I'm going to use this top half to create my model. And I'm going to only look at the data in this blue region. So the first half of my data, I'm only going to use this to train my model. We call this the training data. Can you imagine this model could be anything we've learned so far, like logistic regression? I'm just going to call it logit, or it could be a decision tree. Right, it could be either of these, and I only use my training data to get that model. Now, your first instinct might be, well, Brad, I have double the amount of data, and so by ignoring this bottom half, my model is going to be worse. And you're kind of right. By using less data, the model is not going to perform as well because you're using less data to estimate it. But by leaving half of it out, we're going to be able to estimate how well your model performs in the real world. And this is how we're going to do it. So you're going to create a model through your training data. So step one, so you get your model. Model is estimated from your training data. And just in case you wanted to be visual, remember the training data is the blue one. So you get your model through your training data, and we're going to call this model, let's just call it F. And then, now that we have our model, we're going to predict. So step two, we're going to predict. And we're going to predict on the orange. And the orange is called our testing data. Highlight that orange again, for those of us that want to be visual. We're going to predict on our testing data. Although, as you remember, this testing data also has the y's, right? We have y1 all the way up to, let's say, y100, something like this. All right, so a bunch of zeros and ones. So our testing data, remember, has labels. However, we ignore the labels when we predict. And that is the important part of this validation set approach. Because we ignore the labels when we predict, we sort of have we use our model to estimate what the truth is when we know what the truth is already. So you can imagine what ends up happening is, since we're estimating on our testing data, I end up getting some predictions, right? And I'm going to call these predictions y hats. We like putting hats on things that we predict. Don't worry about that. And let's say my predictions was 1, 0, 1, 1. Right? Well, I know the truth, right? I'd ignored it, but I can bring it back at the end after getting my estimates, and we're going to call the truth y. Right? And maybe for the first one it was wrong, but then I was right for everything else. So I can grade myself just like I would grade you in an exam. Right? So you would notice that this first instance here is wrong, so we're going to highlight that. This is a mistake. Right? But everything else looks pretty good. Right? So you can imagine that now I could say maybe, okay, 1 out of 4 mistakes. And that's my classifier, right? This is literally what I'm doing. I'm counting the number of times that my estimates did not equal the truth. And this is super useful. This allows us to sort of talk about error rates of classifiers, right? And just as a note, when I split the training and testing data, when I split my data to training and testing, I sort of arbitrarily decided to split it at 50%, right? So I picked a 50% split. This is used all the time. It's quite standard, but you can pick any other percentage. You can do an 80% training, 20% test, or anything you think would better suit your problem. So I'll say, however, you can pick what proportion of a split you want to do. In fact, when you do this in radians, it allows you just to move a slider and pick this yourself. Radiant allows you to pick this yourself. Now, another way you can view these errors is through something called a confusion matrix. And this is very useful when you want to look at errors, obviously. Also, when you want to look at specific errors. And by specific errors, I really mean sometimes you care about one type of mistake over another. Because you can imagine when your classifier is wrong, this can happen in one of two ways. This can happen because you had a true y is equal to 1, but your estimate was 0. This is an error. And as you can imagine, I can do the opposite, where you have a true y is equal to 0, but you estimated a 1. These on the outset are probably the same, and it's really difficult unless you have domain knowledge to decide whether one of these errors is worse than another. But I'll say here you might believe one error is worse than another. And if so, you might want to tune one of those error rates to be a bit lower. Actually, this is one of my research areas, so if anyone wants to talk about this more, feel free to ask me. But it would be nice for us to have a way of viewing all of these different types of errors. And this is something you can easily create in Radiant or Excel, and we just call this a confusion matrix. And really, this matrix looks like this box. Oops, let's go back to green. This matrix is a box with 4 entries. It's 4 entries. I'm going to drop them down like here. And what people like to do is they put their prediction on top, and then the truth here. And your truth, the truth was either what? It was either a 1 or a 0, right? So this is, let's say, again, to remember the application we were doing, this could be you get the loan. This could be did not get loan. And then your prediction is also a 1 or a 0. Right? And then you just type in the different types of agreements and mistakes into this matrix. What is this first box here? Well, this first box is just the number of times the truth was equal to 1 and your prediction is equal to 1. Similarly, down here, this is the number of times your prediction was equal to 0 and the truth is equal to 0. And these two are like the entries in the matrix you want to look at for things that are good, right? These are times when you agreed, right? So that's awesome. However, these other off diagonals are times where things went bad. So let's write that in purple. And there are 2 different types of errors, right? So this is the number of times that the truth was 1, but you incorrectly said your prediction was 0. And then here, the number of times that the truth was 0, but your prediction was 1. Right? And this matrix gives you 4 numbers, and just because I can, I'm just going to make up 4 of them. So maybe you got a matrix that look like this. Maybe you got like 100. Then you got 56. Right? These are big numbers, so hopefully this looks good. Then here, maybe you got a 2 and a 4. Right? And so this is kind of what you'd want to see for a good classifier. You want to see that these numbers are really big and the off diagonals are small. But this really depends on what type of problem you're working with and how much error you want to tolerate. And then again, potentially, if you care about this mistake more than this mistake, you might want to make one of those. Those aren't the mistakes. If you care about this mistake more than this mistake, you might want to make sure that one of those numbers is smaller in some sense. And this is a really nice way for us to view errors. So when you're talking to me about the mistakes a classifier can make, I would expect you to produce a matrix like this and talk to me about what each of these errors mean, right? And you can do this for any algorithm. So this works for any algorithm, right? So you can compare a bunch of algorithms using this matrix. So kind of in summary, what you would do when testing how well your algorithm is working, you would do step 1. You would split your data into training and testing. Your step 2, you would estimate the model on the training and predict on test. Then step 3, you're going to show me your errors, show the errors on the testing data using the confusion matrix. And this is going to be a really nice way for us to estimate how well our algorithm is doing, sort of in the real world. And this matrix will give us a nice way to talk about the different types of errors that are happening. And so I would hope that this is the approach you would use when going through any algorithms in the future in this class and really in the real world. If you have any questions about this, please let me know.